2, Polynomials, Basic Operations. We're going to take a look at some adding, subtracting, multiplying, dividing polynomials. What is a polynomial? Well, poly meaning many, the prefix many. You have monomials, which can be just constants. They can be variables. They can be a variable expression like 3x. And when you add or subtract a bunch of those together, you get a polynomial. Now, a polynomial has to have these two components. Its exponents must be whole numbers, can't be fractions, and they can't be negatives. And if you ever have a variable in the denominator, then you have a situation where you have a negative exponent. All right, so real quickly, just to identify or help ourselves figure out what polynomials look like. Remember, polynomials can be a single term. It can be 2, 3, 4, however many. So looking at number 1, we have a 3 term, the highest degree of 3. The highest power tells you what the degree of the function is. In this case, we have whole number exponents, and we have real coefficients, and so this one would be a polynomial. Number 2, we have a binomial now. Highest degree is 1, so this is a linear function. And again, it obeys all of the rules. So it is a polynomial. Number 3, we've got a little problem on number 3. We've got a trinomial with a 1/2 power on that first term, and so that is not going to qualify as a polynomial. On number 4, once again, we have a linear system. We have 1/4 x minus 6x plus 10. So this one is a polynomial. Number 5, no, because of the -2 power. And then number 6, also no, because 2 over x is the same thing as 2 times x to the -1st power. So that does not equate to a polynomial. All right. Our next item of business has to do with that power. But the degree of the polynomial actually gives you a lot of information. It tells you what the shape of the graph would be. It can tell you the possible number of zeros that your graph might have, or x-intercepts. And the highest degree that we have, the highest power or combination of powers, if it's written in a single term, would determine what degree our polynomial is. And we have first degree polynomials are linear functions, second degrees are quadratics, third cubics, and then we have quartics and quintics, and beyond that, 6th degree, 7th degree, and so on. So looking at these, trying to figure out what the degree, we simply go find the highest power. And in this first one, by the way, we try and put polynomials in descending degree order. So we'll probably want to get in the habit of doing that. Number 1 isn't in descending degree order. It starts out with a power of 3, but in reality, it's this power of 7 that determines the degree. So this one has a degree of 7. And that next one, we saw that in the last example. When there is no exponent, we know that that's a first degree function. Also known as linear. Now when you have a term that has 2 different variables, and they in turn have different powers, then what we've got is a situation where I combine the exponents to determine the degree. So we have a power of 2 for the x, power of 3 for the y, and that is a single term right there, which means it's the 5th degree power. Over here, number 4, 4th degree. Once again, on number 5, we've got 3 and 5. So we have an 8th degree number 6, 2, which is called quadratic. And later on, we'll figure out how the degree would help me understand that. We talked about the shape of the graph and how the degree helps you know what's going on in the end. It's called the end behavior, and then what's going on in between the intercepts. All right, combining like terms, a little review from Algebra 1 and order of operations. Remember that in the order of operations, parentheses and exponents, and then with the multiplication, division, the addition or subtraction, it doesn't matter which one we do first, going left to right on the problem. If I come across a multiplication portion of the problem, I would do that first. If I came across a division portion of the problem, I would do that first. And the same thing would go with addition or subtraction. So just be careful with the multiplication, division, addition, subtraction components of order of operations. All right, a few new terms to define here. A coefficient is a number in front of a variable term. An example of that, if I had 3x, 3 is my coefficient. A term is a number, a variable, or a variable expression, which means to have a coefficient and a variable written together, or a variable term of a polynomial. And so the example we had up there, 3x would be a term, a constant could be a term, or just a variable could be a term. And in like terms, they have to have the same variables and they have to have the same exponents, or just constants. They would be the same. All right, a little simplifying. So when we're working with simplifying these expressions, we want to deal with any like terms and we want to put them together. We're going to combine some like terms here. In this first one, we have a little distribution we need to take care of. So thinking about our order of operations, I deal with things within the parentheses first, and if I look at these sets of parentheses, 3x squared minus 2x plus 5, nothing can combine. Same thing with x squared plus 3x minus 7. No like terms there, so nothing to do in the parentheses world. Exponents, there are really none to deal with in terms of the parentheses. So now I get to the multiplication division part, and I have multiplication, I have distributive property right here. So I have 6x squared minus 4x plus 10, and then plus this parenthesis that's around this trinomial here is simply to distinguish it as being a trinomial, x squared 3x minus 7. And then now I look for all my like terms. So again, a like term has the same variable and the same power, which means I have x squareds and x squareds that I'm going to add together, and they'll become 7x squareds. Then I have minus 4x and plus 3x. They are like terms, so I get a negative 1x. And then finally our constants. We have a positive 10 and a minus 7. Negative 7. So we have 10 minus 7 and we get 3. So that would be our simplified expression from these two. 7x squared minus x plus 7. It's a good idea if you're not real comfortable with combining like terms. Maybe you color code them like this, where you draw circles around ones that are the same and then squares or shapes or something to distinguish them. All right, in this next one, we have within this parenthesis here, the larger one, we have some work to do. We have this negative that's going to distribute inside and change all of the signs of that 2x plus 1 quantity. And so I have 3x squared minus 2x minus 1 now within this parenthesis. And once again, we have another negative out here. It's going to change the sign of that binomial. Make it negative x squared plus 1 this time. All right, now I can remove the parentheses and think about all of my like terms. So 3x squared minus x squared gives me 2x squared. Then I have a negative 2x, which is the only x term I have, so that stays. And I have the negative 1 and the positive 1. They're canceling each other out. So I end up with just 2x squared minus 2x. All right. So here now we have two polynomials, A and B. And taking English language and translating it into the math language, subtract B from A. We have to figure out which one are we removing from the other one. And in this language here, subtracting B from A, that means we would start with A, and we would remove or subtract B from it. So that's what subtract B from A would look like in math language. And so I just simply take my polynomial A, and I'm going to subtract. Now when I subtract a polynomial, it's a great idea to remember to put that thing in parentheses, because you're going to have to distribute that sign. Right? Negative, negative, negative. Changes the sign inside of all of that. So this becomes x to the fourth minus 3x cubed plus x squared, negative, negative, positive x cubed plus 2x squared minus 3x. Now you're ready to combine all your like terms. There is only one x to the fourth term, so it stays. There is only one x to the third term. Oh, no, there isn't. There are two of them. So I have negative 3 plus 1, and that gives me negative 2x cubes. And x squareds, I have a positive 2x squared, and then another 2x squared, or x squared and 2x squared, giving me 3x squareds. And then I have a constant of, or not a constant, but a negative 3x variable expression all by itself. And there we go, putting in descending order, descending degree order, 4, 3, 2, 1, and then there is no constant here. I would get that. All right, what about multiplying? And then eventually we'll get to dividing. But multiplying polynomials is just distributive property. And we have talked about before that when you multiply binomials, you can use the acronym FOIL, first terms, outside terms, inside terms, last terms, and work them together. So this is what we're going to do for this first problem. For the second one, where I've got a binomial and a trinomial, I'm not going to do the FOIL thing. I'm going to just simply take each term within the binomial, 2x and negative 3, and multiply it by each term in the trinomial. So let's take a look here at this first binomial. So 2x times 3x, 2x times 2. I have 6x squared. That again comes from 2x times 3x. And then those are the firsts. And then the outside terms, 2x and the 2, giving me 4x. Now we get the inside terms, the negative 5 and the 3x, giving me negative 15x. And then finally the last terms in each parenthesis, negative 5 and the 2, negative 10. So now I have some like terms here. I have 4x minus 15x. So we simply combine all my like terms. 4 minus 15 is negative 11x, and minus 10. And that's what we would get if you multiply those binomials together. All right, just continuing with that process here for this next problem. Again, each term in the binomial multiplies with each term in the trinomial. So I'd have 2x times 3x squared minus 2x times 2x plus 2x times 3. Then I would have the negative 3 multiplying by each of the terms. So minus 3 times 3x squared, minus 3 times negative 2x, and minus 3 times positive 3. Negative. All right. So combining all these, after we simplify here, I get 6x cubed minus 4x squared plus 6x, and then minus 9x squared plus 6x minus 9. And then we look to combine all of our like terms. There is no other x cubed term, so that's going to stay as a 6x cubed. We have negative 4x squared and minus 9x squared, so we have negative 13x squared. And in terms of my x terms, I have 6x and 6x. So they become 12x. And then our negative 9 constant. And we get that. Well, what happens when you have a trinomial? Or a binomial times a binomial times a binomial? Then you take the two binomials and you could multiply them together as a FOIL, get a trinomial, and then proceed to do what we did on the problem just above this one. So we're going to group or multiply first of all the x plus 2 and the x plus 5 together as a FOIL problem. If I did that, I have my x times x plus my 5x plus my 2 times x plus 10. And all of this will get multiplied eventually by the 2x minus 3. So we're going to get x squared plus, combining my like terms, 7x's plus 10. And then 2x minus 3. And then now each term in the binomial multiplying by each term in the trinomial. So I'd have 2x times x squared, 2x times 7x, 2x times 10, and do that negative 3. So negative 3 times x squared, and negative 3 times 7x, and negative 3 times 10. 2x cubed plus 14x squared plus 20x minus 3x squared minus 21x minus 30. Combining all my like terms, there are no other x cubes. I have 14x squared minus 3x squared, giving me 11x squared. 20x's minus 21x's is negative x, and then minus 30. There we are with my combining like terms after dealing with our order of operations. Special products. Binomial squares, also a difference of two squares. So when you have a binomial squared, such as the a plus b squared or a minus b squared, these are what we call our factored form, or we're going to factored form. It's called perfect square trinomials. And what happens here is a plus b squared simply means a plus b times a plus b. And I could FOIL this. Now there's another thing we could think about with binomial squares, and it's a little set of acronyms. STF, TTP, STL. And what these stand for is square the first, twice the product, square the last. What does that mean? Squaring the first means means to take the first term in your binomial and you square it, you get a squared. Twice the product means to take the terms inside of the binomial, the a, and multiply them by b, the second term, and get ab, and then take that times 2, and now we have twice the product of the terms. And then squaring the last takes the last term, giving me b times b, or b squared. So this ultimately becomes a squared plus 2ab plus b squared. And again, it's called a perfect square trinomial. So if you recognize a pattern of something that is an a squared plus 2ab plus b squared, we can factor it to a plus b quantity squared. And with a minus b quantity squared, the only thing that we're going to change is, instead of a squared plus 2ab, this is going to become a squared minus 2ab plus b squared. We always have plus b squared at the end, because if you take a negative b and you square it, you're going to get positive b squared. So those are both perfect square trinomials. This last one is the factored form for difference of two squares. And if I were to FOIL this one out, again, a times a times positive b. And then this next one I have negative b times a. Now a times b, b times a, it's commutative property of multiplication. It doesn't matter the order, so they are the same thing. And then negative b times b. So I would get a squared plus ab minus ab minus b squared. Now what happens with ab minus ab is they cancel each other out. And I end up with what's known as the difference of two squares. This is an important special product. You should be familiar with this one. Get used to it, put it on flashcards, memorize it. So those are a few of our special products. There are some more. And that wraps up the second section of our pre-calculus.